Just like with black and white, as well as grayscale images, we can store color images as bitmaps by storing the value of each and every pixel in the image. However, in the bitmaps we've seen so far, we've only needed to represent the intensity of each pixel, whether on or off or shades in between. And these are readily given a number. For color pixels, however, we need to somehow represent the idea of color numerically. One somewhat limited possibility is to create a table of colors, also known as a palette. It's kind of like an ASCII encoding, but for a set of colors, where we just assign a number to each color. Obviously, there are a lot of colors, but if we just pick a limited set of them and give them numbers, then we have a color table. The numbers are somewhat arbitrary, but we can represent images as bitmaps using these color palettes in the usual way. For each one of the pixels in the bitmap, we just store the value, or the number, that corresponds to the color that we want to display. Palette coloring is useful when we want to make very small color images, because the amount of information we need to store per pixel is just a single number. Having fewer specific colors also means we're more likely to get long runs of identical colors, which means we can use run length encoding to greater effect as well. The problem with palette color, though, is that it doesn't scale very well. If we wanted to represent the fullness of real-world color images, we would need to create a lookup table for millions of colors, and since the numbers for each color are essentially arbitrary, that is, similar colors don't necessarily have similar numbers, then the task of encoding colors from real-world images becomes very difficult as well, and at times disappointing. The solution is to find a better way to represent color. If you've ever looked very, very close at your screen, which I don't recommend doing, then you might have seen each pixel turn into 3 bars of color, one red, one green, and one blue. These are the 3 primary colors of light. You should note that the primary colors of light are different than those of paint or pigment. When adding paints together, as you mix more and more colors, the paints get darker and darker, eventually leading to black when you've added all the possible colors. When dealing with the color model of light, though, since we're projecting these colors through a screen eventually, the more light you add, the brighter it becomes. When you have no light, you have no color, and that's a black pixel. When you mix all 3 primary colors together, so red, green, and blue, at maximum intensity, you get white light. This is the RGB model of color. So every color is described as a combination of the intensity of its 3 primary color channels. As some examples, if all 3 channels are 0, that's no light, so black. If we increase the intensity of just the red channel, that gives us shades of pure red. If instead we increase the intensity of the green or blue channel, then we get shades of green or blue, respectively. If we use the red and green channels together, we can make yellows, oranges, and browns. If we use the red and blue together, then shades of pinks and purples appear. And if we use all 3 channels, we can reach the shades and colors in between. Note that when all 3 channels are the same value, so when red and green and blue are all equal, then the result is a shade of gray. All 3 set to a low value is a dark gray to black, and if all 3 are set to the same higher value, then we get light gray to white. Now you don't need to memorize all the possible combinations, but to understand color images, we need to understand that color itself can be described by a combination of 3 numbers, representing the intensities of the R, G, and B channels. A question remains though, how will we store these 3 channels? How many possible values should each channel be able to represent? One answer is to use 8-bit color. 8 bits, as we've seen, is 1 byte, so in an 8-bit color bitmap, we store 1 byte of information for each and every pixel in our image. That 1 byte then needs to be divided into 3 parts, representing each of the 3 channels. Unfortunately, 8 bits doesn't divide evenly across 3 channels, so we get 3 bits for red, 3 bits for green, and the remaining 2 bits for blue. With 3 bits, we can represent 8 different shades of red. Another 3 bits for green independently represents 8 shades of green. And just 2 bits for blue means only 4 possible shades of blue. Now we can combine these reds, greens, and blues in various ways, for example using lots of red and blue but not green, or a little bit of each. So in total, with 1 byte per pixel like this, means we can represent 8 times 8 times 4, or 256, possible combinations or possible colors. Images with fewer than 256 total different colors can work well for things like pixel art or other simple, vibrant color schemes. But it also provides a good enough range of color for applications where fast speed and small memory are more important than having highly detailed images. So applications like remote desktops, retro video games, or embedded systems like a toaster with a display screen might still use 8-bit color to this day. However, it's not a great format for representing things like photographs. Real color gradients can end up looking grainy or flattened in 8-bit color. So to get a better looking image, we'll need to be able to represent more possible colors for each pixel. Now, human eyes can distinguish between about 1 million to 10 million different colors, according to varying studies. This is because human eyes have 3 types of cone cells, specialized for red, green, and blue wavelengths of light, respectively, each of which can distinguish in the ballpark of around 100 different color shades. Everyone's different. Some people are tetrachromatic, for example, but this gives us a rough idea of how much information we need to represent to have a pretty realistic looking image on a computer screen. So 24-bit color, or true color as it's sometimes called, uses more storage space per pixel, but achieves more realistic looking images. 24-bit color uses 1 byte per channel, totaling 3 bytes for each and every pixel in our image. That's 1 red byte, 1 green byte, and 1 blue byte, which combine to make a single pixel. So 8 bits times 3 is 24 total bits per pixel, hence 24-bit color. If we have 1 byte per channel, that means we can represent 256 possible shades of that channel alone. So 256 different shades of red, green, and blue independently. When we combine them together, that's 256 times 256 times 256, or over 16 million possible color combinations per pixel using 24-bit color. This is sufficient for fooling most human eyes. Describing a color in this color scheme means providing 3 numbers in the range 0 to 255. For example, the color green would be 0, 255, 0, and white would be 255, 255, 255. And the color here, 255, 27, 7, would be some shade of mostly red. If we're to make a whole bitmap image with 24-bit color, then we have to store 3 numbers, 3 bytes, per pixel. If we write all of that out, you can see the amount of information we need to store to represent this simple image has increased significantly as compared to grayscale bitmaps or even palette color. However, that increased storage means we can represent more information, more possible colors. Another way to say this is the information space for each pixel is now larger. Note that it takes the same amount of information for each pixel in our bitmap, no matter which specific color we choose to represent. Ultimately, storing a fully black image where all the pixels are just 0, 0, 0 takes the same amount of space as storing a bitmap representing a Picasso that has the same dimensions. Now, very often, instead of listing 3 separate numbers, you'll see color values represented as a short 6-digit code called a hex code, something like this. These are called hex codes because they're hexadecimal numbers, and they're used because they give us a more succinct way of representing the same information. Hex codes don't change how we're storing the colors, but they do make colors easier to work with for humans. They may look random at first, but they're just another way of writing the exact same RGB values in another numbering system. Hexadecimal, or hex for short, is the base 16 numbering system. Like decimal or binary numbers, hex is just a different base for representing the same numerical ideas. Recall that binary is base 2, and so it has 2 symbols, 0 and 1. Decimal is base 10, and so it has 10 symbols, 0 through 9. Recall also that in binary it took more bits to represent the same information. Fewer symbols means we need more digits to represent those same numbers. So if we go in the other direction and pick a base that's bigger than 10, like say 16, we can represent the same information more compactly with fewer digits. Ultimately, that's true of any base number that's larger than decimal, but we pick 16 because it's a nice power of 2, which ends up being helpful later on. So hexadecimal is base 16, and that means it has 16 symbols. To represent this, we use the symbols 0 through 9, and then we borrow A through F from the alphabet. So A in hex means 10 in decimal, B means 11, C is 12, etc., up to F, which is 15. So in a single column, we can represent the numbers 0 through 15 with a single digit. But now, if we add more digits, instead of becoming 10 times larger, each new column is 16 times larger than the last. Let's look at an example. So if we count up from 0 in hex, for the first 10 numbers, it looks the exact same as decimal. But after that, instead of needing a new column like we do in decimal, there's still room to make our ones column larger. So after 9 comes A, and then B, then C, then D, all the way up to F. At that point, we've counted the first 16 numbers from 0 to 15. If we add one more, that column is full and it spills over. So just like in our other 2 numbering systems, that becomes 1, 0. And then we continue to count. 1, 1, which means 1 from the 16s column and 1 from the 1s, so 17 in decimal. Then we have 1, 2, 1, 3, and so on up to 1, 9. And then we have 1A, which means again 1 from the 16s column and A, or 10, from the 1s column. So 16 plus 10 gives us 26 in decimal. 1B, 1C, etc. up until we get 1F. Now after we get to 1F, we spill over again to get 20. So that's 2 16s, or 32 in decimal. We can keep counting up this way until we get to FF, at which point we'd spill over into a new column, 100. Notice that counting works the same way in all three bases, but it looks different because of how many symbols we can use. So with a single hex digit, we can represent the numbers between 0 and 15. With a second digit, we can represent 16 times more numbers, or up to 256 possible values. Sound familiar? So there's a reason we use base 16 specifically, instead of say base 14 or 20, and it's because 16 is a power of 2. This means that it maps neatly onto binary. 16 is 2 to the exponent 4, so one hex digit is the same size as 4 binary bits. This means that 2 hex digits equals 8 bits, or 1 byte. So we can succinctly represent 1 byte using 2 hex digits. So for true color, where we need to store 1 byte for each of the 3 channels, means we can use 2 hex digits per channel, something like what we see here. And this is why hex codes have 6 digits. 1 byte per channel is 2 hex digits each, times 3 channels for R, G, and B. This shorthand between binary and hexadecimal means that hex values show up often in computing. Anywhere where we want to describe bytes of binary without having to lay out a bunch of zeros and ones, we can just use a couple of hex digits instead. Coming back to our working 12 by 12 bitmap example here, if we described it with hex codes, it looks like this. A little bit more consistent compared to the RGB decimal values, so it's a little bit less challenging to read and compare colors. But remember, this is just a different way of writing the same information. Each pixel, in 24-bit color, still needs 3 bytes of data and still gets stored in binary. Hex codes are, again, just a nicety for humans. Now, when scaling up from small images like this to high-resolution bitmaps, needing 3 bytes of data for each and every pixel means the amount of data grows rapidly. A 4K bitmap in true color requires almost 200 million bits, or around 25 megabytes, to store in memory. By comparison, the Apollo moon landing mission used about 75 kilobits of memory. So we would need about 300 Apollo modules to store one 4K bitmap in 24-bit color. Because of this, compression of our image data becomes crucial. We could try to apply run length encoding, but with 16 million possible color values per pixel, the chances of getting long runs of identical colors is greatly decreased. To that end, more complex forms of compression exist for modern images. We won't go too deep into the specific details of how they work, but for example, JPEG encoding, or the Joint Photographic Experts Group format, works in a way that's similar to averaging the values around each pixel. In that way, we need to store less information because it's as though our image is actually smaller. This is an oversimplification of the actual JPEG algorithm, but it's a similar idea. JPEG approximates colors and blends areas together, sacrificing some detail in order to achieve much smaller file sizes. This is known as a lossy form of compression because when we encode the image, some information is lost forever. There's no way to pull apart the pieces of an average pixel to get the original data back. Compare this to run length encoding though, where we can easily reproduce the original bitmap. All we need to do is take the length of each run and use that to count out copies of the value. The lossiness of JPEG encoding can oftentimes be seen in the image itself as little aberrations or artifacts, like lines or edges that look blurry or flattened gradients of color. There are also levels to JPEG encoding, so someone using professional software to make a JPEG image can trade off better quality for larger file sizes, as necessary. PNG encoding, or the Portable Network Graphics encoding, is a lossless form of image compression by comparison. It works similar to run length encoding, but with more steps and dimensions. It can compress repeated patterns from throughout the image, and it assigns similar values to more frequently used colors in order to achieve a pretty good standard for compression. PNG, or PNG images, have an optional fourth channel called alpha, so RGBA, which encodes transparency into the image as well. This can be useful when you want to display one image on top of another, but this requires an extra byte per pixel, and so increases the file size as compared to JPEGs, which don't support transparency. So if you compare a JPEG and a PNG of the same image, the PNG will usually look nicer, but also be quite a bit bigger. In this displayed example here, for one, the PNG is about 10 times bigger, but if you look closely at the JPEG image, you can see small distortions in color. This is a very emphasized example of JPEG artifacts. In practice, oftentimes, the two images might be difficult to distinguish at all. By contrast, if you compare a PNG to a bitmap, they should look identical because the PNG is lossless, but the PNG should have a smaller file size than the full uncompressed bitmap image. As an uncompressed bitmap in true color, this example image would be over 16 megabytes, nearly 4 times larger than the encoded ping here. Depending on your purpose for the image in question, different encodings may have more or less value to you. For example, if the image is to be displayed on a web page in a relatively small size, then the loss of detail from highly compressed JPEG images might not matter that much, while smaller file sizes would be helpful with quickly transmitting over the internet. Conversely, if you're considering topographical maps or satellite imagery, the very small details will be important, and so a lossless compression like ping would be better suited. 2 other common formats for images that you'll likely see out in the world include GIF, or GIF if you're like that, and scalable vector graphics. The GIF format allows multiple images to be compressed together into an animation using a limited palette and comparing similarities between frames in order to save space in a very lossy way. It's a bit like a flipbook where displaying a series of static images gives us the illusion of movement. Scalable vector graphics, or .svg, store images according to their underlying lines and shapes rather than by individual pixel values. What this means is vector graphics are scalable. So if you take a bitmap image and stretch it to double its size, for example, then each pixel becomes a block of 4 pixels. This leads to a blurry or pixelated looking image. Vector graphics, on the other hand, can just recompute the output shapes for the larger scale, resulting in a sharp-looking image at any size. The point of all this is just layers of abstraction on top of the task of storing information in digital memory. Now, at this point, we've seen that everything in a computer is ultimately stored in binary. How we accomplish that is through decomposition. We divide and encode whatever complex information we're trying to store until we have a numerical or binary representation, which will work in computer memory. We saw how to convert decimal numbers to binary directly and back again. We saw then that floating point numbers can be stored as a combination of 2 whole decimal numbers. We saw that we can represent text as numbers using the ASCII encoding, for example. Technically, computers can go straight from text to binary, but conceptually, we saw this as turning text into decimal numbers, which can then be translated into binary. We saw that images can be decomposed into a grid of pixels, which represents singular colors each, which can be represented numerically using the RGB encoding. Even audio and video files are stored as binary. Sound is stored in binary by sampling audio waves at regular intervals, somewhat like breaking a song down into individual music notes. Each sample is then assigned a numerical value indicating its amplitude, which is then converted to binary. And video files, like movies, are decomposed into a series of images called frames, which are played rapidly to create motion and stored alongside an audio track. The frames and audio track are then both subsequently decomposed down as we've seen, encoded as numbers, and stored in binary. In the end, every digital experience, every spreadsheet, every song, every movie, every video game reduces to the same foundation, a structured sequence of zeros and ones. When listening to songs or typing floating point numbers into a spreadsheet, though, we don't need to know any of the associated binary values. The details of how our information is stored is mostly hidden away through abstraction, and we're free to work with our information at a more meaningful level. But what really makes data meaningful isn't just what's being stored, but also how we interpret it. If everything in memory is stored as binary, then when we try to read our data, the computer needs to know how we expect it to be structured into those more meaningful forms. For example, consider this cat GIF. Again, the computer doesn't understand what cats are, it just sees some binary data, and an instruction to display that data as an image. The file type here is .gif, which tells the computer how it expects that data to be structured into a compressed grid of pixels with multiple frames. It also tells the computer which program it should try to use to interpret and display that information. However, we can deliberately misinterpret that information, say by assuming that it's a text file. So let's open this GIF in a text editor and see what we get. As we can see, there's a lot of data here. Over 59,000 lines of text, but it doesn't make any human sense. When we try to read through it as text, it's just garbled. What's happening is that the binary bits making up this image are being misinterpreted, decoded as though they were ASCII or UTF text instead of as an image file, but the data itself hasn't changed. So is this a cat, or a meaningless stream of garbled text symbols? Or is it neither? The answer isn't in the data, it's in the interpretation. In the end, computation isn't just about storing data, it's about making meaning from it. It's how we take the vast amounts of information in our world, break it into discrete computable parts, and then structure and interpret those parts to answer our questions and solve our problems. You can think of it like a calculator, but instead of just adding two numbers to get a sum, computation lets us process text, recognize faces, recommend movies, and even predict the weather. Computation transforms raw data into something useful. In the next chapter, we'll start working with Python programming to see how that process works. For now, though, that's it for this video. Thank you for watching. Don't forget to blink, and I'll talk at you in the next one.